Welcome to G Fun Facts Online. The ground beneath your feet feels solid, right? Stable, unmoving. But that's an illusion. Our planet's surface is in constant, slow-motion. It's a mosaic of massive rock slabs, miles thick, grinding against, pulling away from, and crashing into each other. This is the story of plate tectonics, the engine that drives nearly everything geological on Earth, from the highest mountains to the highest peaks, and the earthquakes and volcanoes that constantly remind us of its power. This isn't just a theory, it's the unifying framework for understanding Nashi dynamic planet. Let's travel back to the early 20th century, to a German meteorologist named Alfred Wegener. In 1912, he proposed a radical idea he called continental drift. He wasn't the first to notice that the coastlines of South America and Africa seemed to fit together like giant puzzle pieces, but he was the first to build a serious scientific case for it. He argued that today's continents were once part of a single, massive supercontinent. Wegener gathered a surprising amount of evidence. He found fossils of the Mesosaurus, a freshwater reptile, in both southern Africa and South America. How could this small reptile cross the vast Atlantic Ocean? The simplest answer was that it didn't have to. The continents were once joined. He also pointed to rock formations and mountain ranges. The Appalachian Mountains in North America, for instance, matched up perfectly with mountain ranges in Greenland, Ireland, Britain, and Norway, suggesting they were all once a single, continuous belt. He even found evidence of ancient glaciers in places that are now tropical, like India and Australia, indicating these landmasses were once much closer to the South Pole. But despite this compelling evidence, the scientific community largely dismissed Wegener's idea. The biggest problem was that he couldn't provide a convincing mechanism. How could colossal continents possibly plow through the solid rock of the ocean floor? The forces he proposed, like the Earth's spin, were proven to be far too weak. For decades, continental drift was considered fringe science. The revolution came in the mid-20th century, thanks to technology that let us explore the ocean floor. Using sonar, scientists discovered a massive underwater mountain range running down the middle of the Atlantic Ocean, the Mid-Atlantic Ridge. They found it was volcanically and seismically active. Then came the clincher, paleomagnetism. When volcanic rock cools, magnetic minerals inside it align with the Earth's magnetic field, like tiny compass needles. We know the Earth's magnetic field has flipped its polarity many times. On the seafloor, scientists found a stunning pattern. Stripes of rock with normal and reversed magnetism, perfectly mirrored on either side of the Mid-Atlantic Ridge. This was the smoking gun for a concept called seafloor spreading, proposed by Harry Hess. New oceanic crust was being created at the ridge and being pushed outwards, like two giant conveyor belts moving in opposite directions. Finally, when detailed global maps of earthquakes and volcanoes were created, it was undeniable. These events weren't random. They occurred in narrow, distinct bands that outlined the edges of massive plates. The ideas of continental drift and seafloor spreading merged into the comprehensive theory of plate tectonics, and by the late 1960s, it had become the cornerstone of modern geology. So how does this all work? First, we need to understand Earth's structure. The Earth's rigid outer shell is called the lithosphere. It's made up of the crust and the very top part of the mantle. This lithosphere is what's broken into the tectonic plates. Beneath the lithosphere is the asthenosphere. It's not liquid, but it's so hot and under so much pressure that it behaves like a very thick, slow-moving fluid, kind of like caramel or putty. This ductile layer is what the rigid lithospheric plates slide on top of. Think of the lithosphere as the cracked shell of a hard-boiled egg and the asthenosphere as the slightly soft, cooked white underneath. The shells can slide around on that softer layer. The Earth's surface is broken into about 7 or 8 major plates and many more minor ones. The Pacific Plate is the largest, almost entirely oceanic. Then there's the North American, Eurasian, African, Antarctic, Indo-Australian, and South American plates. They are all moving at about the same speed your fingernails grow, just a few centimeters per year. But over millions of years, that adds up to thousands of kilometers. What drives this motion? It's all powered by heat escaping from the Earth's core. This heat creates slow-moving convection currents in the mantle, where hot rock rises and cooler rock sinks. But it's not as simple as a conveyor belt dragging the plates. The two main driving forces are actually gravity-based: slab pull and ridge push. Slab pull is the star of the show. This happens where a dense oceanic plate collides with another plate and sinks into the mantle, a process called subduction. As the cold, heavy edge of the plate, the slab descends. Its sheer weight pulls the rest of the plate along behind it. It's like a heavy anchor pulling its chain down into the water. Ridge push is a secondary force. At mid-ocean ridges where new crust is formed, the area is elevated because of the hot, rising magma. As this new rock cools and gets denser, gravity causes it to slide down the gentle slope of the ridge, pushing the plate away from the center. Now for the most exciting part, the boundaries where these plates interact. This is where, the geological action happens. There are three main types. First, we have divergent boundaries, where plates are moving apart. Most of these are on the ocean floor, forming the mid-ocean ridge system. As the North American and Eurasian plates pull apart, magma rises from the mantle to fill the gap, creating new oceanic crust. This is seafloor spreading in action. This process can also happen on land. The East African Rift Valley is a prime example, where the African continent is slowly being torn in two. If it continues, a new ocean basin will eventually form. Second, we have convergent boundaries, where plates collide. What happens here depends on what types of plates are involved. When a dense oceanic plate collides with a lighter continental plate, the oceanic plate is forced to subduct or slide underneath. This creates a deep oceanic trench. As the subducting plate sinks, it heats up, releasing water, which causes the mantle above it to melt. This molten rock, or magma, rises to form a chain of volcanoes on the continent. The Andes Mountains are a perfect example of this, formed by the Nazca Plate subducting under the South American Plate. These zones also produce the world's most powerful earthquakes, called megathrust earthquakes. When two oceanic plates collide, the older, colder, and denser one subducts beneath the younger one. This also creates a trench and a chain of volcanoes, but this time they form as a volcanic island arc. The Mariana Islands and the deepest spot on Earth, the Mariana Trench, are the result of this type of collision. And what happens when two continents collide? Since continental crust is thick and not very dense, neither plate wants to subduct, so they have nowhere to go but up. The immense pressure buckles, folds, and shatters the crust, creating enormous mountain ranges. The Himalayas, the world's highest mountains, are the result of the ongoing collision between the Indian Plate and the Eurasian Plate. The third type of boundary is a transform boundary, where two plates slide horizontally past each other. Crust is neither created nor destroyed here. The movement isn't smooth. The plates lock up, build stress, and then suddenly slip, causing an earthquake. The most famous example is the San Andreas Fault in California, which separates the Pacific Plate from the North American Plate. These plate interactions are responsible for most of Earth's geological drama. Earthquakes are the sudden release of energy when plates slip past each other. The most powerful ones, as we said, are at convergent boundaries. Transform faults like the San Andreas also produce powerful shallow quakes that can be extremely destructive. Volcanoes are also concentrated along these boundaries. The famous Ring of Fire around the Pacific Ocean is a direct result of subduction zones all around the Pacific Plate, leading to intense volcanic and seismic activity. However, not all volcanoes are at plate boundaries. The Hawaiian Islands, for instance, formed over a hotspot, a plume of superhot mantle, rising from deep within the Earth. As the Pacific Plate moves over this stationary hotspot, it creates a chain of volcanoes. The island of Hawaii is currently over the hotspot and is active, while the older islands to the northwest are extinct. And of course, there's mountain building. We've seen how continental collisions create massive fold mountains like the Himalayas. Volcanic arcs create ranges like the Andes. Over geological time, this process repeats in what's known as the supercontinent cycle. Around 335 million years ago, all the continents were fused into one giant landmass called Pangaea. As the plates continued to move, Pangaea broke apart, and the continents drifted to their current positions, opening oceans like the Atlantic. The cycle of continents coming together and breaking apart has profoundly impacted Earth's climate and the evolution of life. Today, we can track these movements with incredible precision using GPS. Scientists can measure plate motion down to the millimeter. We also use seismic tomography, which uses earthquake waves to create 3D images of the Earth's mantle, allowing us to see the convection currents and subducting slabs that drive the whole system. The theory of plate tectonics revolutionized our understanding of the planet. It's the grand, unifying story that explains why we have continents and oceans, why earthquakes shake our cities, why volcanoes erupt, and why great mountain ranges touch the sky. It's a reminder that the ground we stand on is part of a slow, powerful, and ongoing dance that has been shaping our world for billions of years. Thanks for listening to G Fun Facts Online.